Hello, we are Team 2 with Brian Nima, Mai Tùng Dương, and me, Trần Minh Tuấn. And today I will talk about our project in reinforcement learning with augmented data. And let I remind you a little bit about the reinforcement learning. When we have the agent and the environments, when the agent in the state and it touch the action, it will be get the reward from the environment and move to the next stage. But the reinforcement learning suffers from two main problems. The first one is poor data efficiency. As you can see, when the agent in the state execute the action and get the reward from the environment and move to the next state, then if we start the another action and get the reward and move to the another state, this learning process has many iterations, and we need to find the way to learn the policy more efficiently. And the second problem is the poor generalizability. If we change the agent in the one environment, so how we can deploy it in the different one? So for example, when we change the agent in the lab setting, so how you can make them work in the real world setting? To address the problem in the computer vision view, it will be they usually use the data augmentation. The augment dataset is formal data points and making the pair out of existing data. And in recent years, there are several methods that apply the augmentation in the reinforcement learning. For example, the curl or the DIQ, but their method are not brought to play. They only apply for one specific method. On the other hand, our choice method, the reinforcement learning with the augmented data or brush, is the model of notice methodology, and it can be used alongside any reinforcement methods.
So the way that we replicated this paper is that we focus on the DeepMind control suite, which are the environments that are more robotics related. And we actually replicated results in 4 environments: Cardpole, Walker, Cheetah, and Ball and Cup. We trained the agents for 200,000 training steps to try to balance feasibility and how many results you would get. We focus on 4 augmentation methods: crop, grayscale, cutout, and color jitter. And we ran all of our experiments in a Docker container, which is an isolated environment similar to a virtual machine that virtualizes an operating system. We had to do that because our distro, right, our Linux distro was not actually working well with MuJoCo. These are some of our results. So what we found is that crop is actually the best augmentation in the Cardpole environment, similarly to color jitter, right? Our results are really similar to the paper. In the case of Walker, we found that crop is way better than all the other augmentations, and our results are even better than the ones reported in the paper. We can watch here the case of like crop on top and cutout in the bottom, and we see that the cutout one does not learn, while the crop one actually learns how to walk quite well. These are the results in the Cheetah environment. In this case, crop, it's really good, while the other ones are extremely bad. So there's a really big difference between crop and all the other augmentations, or no augmentations at all. In the case of Ball and Cup, we find similar results. Crop is again the best augmentation. Considering the importance of crop, we also ran combinations of crop with other augmentations. So for instance, crop grayscale, crop cutout, and crop color jitter. The authors actually report these results in one of the environments, Walker. We actually conducted these experiments in all the 4 that we focused on. And in the case of Cardpole, we saw that actually adding an extra augmentation did not add anything to the results. We can also watch here the crop one on top and crop cutout in the bottom, and they actually learn at the same time, and the final results quite similar. These are the results in the Walker, and this is actually the only environment where adding an extra augmentation actually improves the agent, right? All the combinations actually are better than crop. In the case of Cheetah, crop was again the best augmentation, followed quite closely by crop grayscale. In the case of Ball and Cup, similar to the Cardpole, we see that actually adding an extra augmentation does not add anything to the training of the agent, right? So they actually achieve a similar level of reward.
So first, we try some additional augmentations, which is smoothing, sharpening, and sobel filter. Smoothing is very similar to apply on a blurry camera. Sharpening highlight the edges, which is inspired by the author's discussion, and sobel filter is as edge detection mechanism, which is also inspired by the author discussion. And we do experiment with these simple novel augmentations in 4 environments that we focus on, but the result is not very promising. All of their novel augmentations doesn't perform better than their no augmentation, and it by far much worse than their the random crop. And let's watch a visual example. We can see that like the agent doesn't really learn well. It cannot like balance well. It cannot run very well. You can see. And given the importance of cropping, we we have the intention to do some object detection crop. Basically, we use few-shot learning, which is a learning algorithm from just a few training examples per class. And using this mechanism, we used the image of the agent as novel class, and we expect that when deployed to the environment, it can detect the agent. And then we will crop the image based on the center of the detected box. But we realized that this takes a lot of time. It leads to 1,555-fold increase in time, and is basically not feasible to run. Yeah, that's why we try to do some approximations. We do 2 approximations. The first one is standard deviation-based saliency crop. Standard deviation is approximated by the square distance between the image and its blurred version. And we find the region with the highest standard deviation and use it as a center of cropping. This leads to a slight increase, only 1.3-fold increase in time, and is feasible to run. The second one is a pre-trained saliency crop, which have a function to detect saliency map. As you can see in the example here. And the saliency part will be the part that is like the main content of the image. And the maximum saliency pixel is used as a center of cropping. It leads to 12.5-fold increase in time. So it actually like increase the time complexity quite a lot, but we still want to try it. So we decide to apply the second one only in one setting, which is couple setting. And the result is here. Even though saliency crop is better than standard deviation based cropping, it doesn't perform better than no augmentation, and it's performed much worse than random cropping. In other environment, let's watch a visual example. We can see that like the couple doesn't really balance well in both cases. In other environments, when we do experiment with standard deviation-based cropping, we realize that like the result is not better and sometimes worse than the no augmentation, and in all settings is far worse than the random cropping.
So overall, results were not really promising, unfortunately, right? Crop was still the best performing augmentation as reported in the paper. Our newly proposed, like really simple augmentations did not help. And we actually tried to create a new kind of cropping, right? We wanted to do this object detection based one. However, they were not feasible in time. So that's why we actually created a few approximations that were inspired by crop. However, they were also worse than no augmentation. So we tried these like these variations of crop, right? To actually crop the image in the best place ever, right? Like in the best place possible, sorry. And we actually have some ideas, like we have some hypotheses to why it actually failed. It may well be that our approximations were not good enough, so that's why we got bad results. It could be that actually having random crops, like bad crops, teaches the agent to ignore like empty parts of the image, right? So they are kind of like adversarial examples. Also, it could possibly be that like the dropped parts of the agent that were important. So we actually learned a lot from this project because we actually faced many challenges. We learned that like our ideas do not always work, and improvement might take a long time, as we actually felt. And also extending other people's code bases is quite challenging. Some possible future steps are, for instance, how can we make augmentations more efficient? Augmentations aim to increase efficiency, right, in the training process, but actually running them might take a lot of time. Another possible future step is how can we approximate these object detection algorithms, and how can we improve crop, right? As I said before, actually having bad crops might be useful adversarial examples. So how can we actually improve random crops? Thank you very much for listening, and bye-bye.